This is Dylan Sieverts going over chapter 15 homework. Starting with number 1, we know that our formula with relation to angular acceleration and angular velocity and time is right there at the top of the page. And so from that point, we can solve for t. And then we get the following because we know that the angular momentum at a certain point is the radius from your origin or where you're taking it to the point you want to find that angular momentum at. And so we basically combine those two formulas in order to get that relationship of angular velocity of b over the angular acceleration with respect to the radius of b and radius of a. And so basically we found that formula and then plugged in the different ratios of the different sizes of the pulleys. And that gave us what the time was at that instantaneous time of the bell at the at each position. Okay, number 2. This one, we know the relationship of theta being the h over the radius. And so, let's see. I did these ones last week. So we were able to calculate the change in theta and then use the same formula as above, where our angular velocity is related to our tangential velocity times by however many rotations, and we had to do that conversion. And from that point, we were able to get a similar formula as above, where the change of t is change in theta over the angular momentum. And we're able to get the total time after we took the magnitude of that. Number 3, these ones I'm understanding a lot better. Basically have our standard formula where we have a instantaneous center, and then that basically goes to 0, or I guess that would be a no-slip equation, which is below. So we have VB equals VA over the velocity with respect to B and A. And then we take the cross product of that, which is your angular velocity times your radius from B to A. We find those components, take that cross product, and then we have the left and right side that each have their own components. We make those equal to each other, so we have our I and J components separate. From there, we're still missing something because we have 3 unknowns, so we need 3 equations. And so from that point, we want to find the velocity at C so that we can find the velocity at A, because we have more information about velocity C. And we do the same thing. VC is equal to VA over velocity C to A. Take the cross product there, get the right side of our equation, and with what the problem gives us. With the left side, we were able to get our x component, and let's see. Yes. And then from that point, there's enough knowns to where we know our x component of our velocity at point A, and we're able to plug that into the previous I equation above that's circled, and that allows us to find our total angular velocity. And then from that point, part B asks for the velocity at point B. We are able to find that because we have the x and y component. Okay, number 4 is basically the exact same thing. However, there's just a bunch of different geometry to it, since certain things are moving in different directions. But basically we're able to find, we want to do everything with relation to D because we have the most information about D. So we first are trying to find the velocity of A with relation to D. So you can see the formula there. I take the cross product, plug everything in. And then from that point, we're able to say that, let's see. Oh yeah, then we just solve for VA since certain I and J components add and subtract to get that, and then we know that our angular momentum is always going to be in the K direction. And then for part B, so we were able to solve for the angular the angular velocity from A to D first, and then plug that back into our VA equation. For part B, we want to take the velocity at point B, and we have a lot of information about point D because we found the y component of that. And we take the cross product with relationship of the radius from B to D and the angular momentum, which we had previously. And then we add our components, take the magnitude, and we get VB. Number 5, it's pretty much the same thing, just different geometry again. This one was a little bit more confusing because we had to basically say that, take it in relationship to P and Q is what they were named when that velocity was 0, so that we could find our unknowns. It basically follows the same steps as the previous one. Number 6, we had to look at each gear individually. We had the most information about gear B, and that was also in the center, so we took everything in relationship to that. We were able to find our y components of velocity at A and C, and then we know that our formula, angular velocity, is equal to velocity over our radius, but in this case we can change that to just the length between C and B and A and B, and then we were able to find the instantaneous centers using that formula, subtracting the difference and dividing it by the overall radius. And the angular velocities. Moving on to number 7. This one is very similar. We take our angular velocity formula and plug everything in, and we know that the angular acceleration goes to 0 when we make an instantaneous center point. So we were able to find the acceleration at b, the normal acceleration, and we're able to then solve for alpha. Then we were able to use that alpha to plug that back and find the acceleration at point A. And number 8, basically same thing. We use our acceleration formula, where the acceleration of A with respect to an instantaneous center, and we know that wherever we're taking our instantaneous center at becomes 0, and we're given the rest of the info. We plug that in to find alpha, and then we're able to rewrite other instantaneous acceleration equations to find the acceleration at each different point. That involves taking the cross product and basically using that formula from the notes. Number 9, I was unable to finish, but I just need to do a bit more practice with motion in 3 dimensions. But I was able to use the law of sines to find the lengths of each side. And then we have our normal acceleration, angular acceleration with respect to p, which is moving in 2 different directions. I just wasn't sure if I was doing this correctly, and I tried it a few times with my study group, and truly I just wasn't understanding it. And I spent too many hours trying, so I want to understand that one, but not sure if I will. Give me credit for whatever you wish. Number 10, this one was more straightforward to me because we have this specific formula and we're able to plug everything in, take the cross product like we did in the previous problems. And then we would just basically plug that in with relationship to P, because that's the point moving along the wheel at any point in time with the 2 rotating axes. And then we're able to find our acceleration in relationship to where that point is. And that was it.